Hey guys, this is Miss Dolan, and today we're going to be talking about transformations and rate of change of quadratics. Okay, first off, we are going to look at the transformation equation, and you guys should look at this as it being familiar because you already know what the vertex form is. Well, the vertex form also describes certain transformations of quadratics. Okay, so, and by transformations, I mean that our parent function looks like this. This is x squared. Sorry, it's not perfect. But our quadratic equations and parabolas can flip and be translated and rotated, etc. And this equation describes that. So, as you can see, A indicates a reflection across the x or the vertical stretch or compression. Okay, so if A is negative, then that means that your parabola is shifted downward. So just like this green one over here. So, and that's if it's negative. So if it's negative, negative means that it's reflected across the x. Okay, and also if A is a fraction, then that means that it's compressed. So that means that it gets wider. Compressed means like, it's kind of like a fat parabola. And then if it's vertically stretched, that means that it's a number greater than 1. Okay, and that means that it's skinnier. So it looks like a skinny parabola. Okay, so we also need to talk about the h. And what I told you guys before is that the h and k represent the vertex, but they also represent the horizontal shift and the vertical shift. So h represents the horizontal shift, and remember that this is always the opposite. So say it's -3. It's obviously +3 because it's the opposite. And then the k represents the vertical translation. Okay, and the vertex of the parabola is that hk. So I'm going to give you some example problems so that you guys actually understand. When you have to describe an equation or a transformation, you're going to be given an equation and you have to describe exactly how the transformation is going. So here's my example equation. And if it says f of x equals negative x minus 5, and then I'm going to do plus 6. Okay, so if I had to describe this, I would say because it's a negative, then it's reflected over x. So it's going to be reflected over x because it's negative. And then we're going to look at the horizontal shift. Okay, this is the horizontal shift. Well, regularly, if this looks like a -5, but we have to think about it like it's actually a +5. So on a number line, if we were thinking +5, we're thinking to go right because that's the positive way. So we're going to think about this as +5, and we're going to think that we're going to shift it right by 5. So we shift that right horizontally by 5. Okay, next we're going to talk about the vertical shift. The vertical shift is always at the end. And this is always true. It's not the opposite of what you think. So this, you're going to shift vertically up by 6. So each piece of the equation tells us, whether it's reflected over x or if it's just normal. If it's shifted horizontally, and then if it's shifted vertically. Okay, here's my next equation. It's f of x equals 2 times x plus 4 squared minus 5. Okay, this is talking about our stretch or compression, and this is a stretch. So when we describe it, we're going to say it's stretched by 2. Okay, next, we're going to talk about our horizontal shift. Okay, and that's the opposite of what we think it is. So it says +4, but we're actually thinking of a -4. So it's going to be horizontally shifted so horizontally shift left by 4. Okay, next we're going to look at the vertical shift. So this vertical shift is accurate. It's not the opposite. So the vertical shift is up. No, actually it's down. It's negative. So it's a vertical shift down by 5. Okay, so you just have to keep in mind that each part of the equation represents something. So the number out here is going to tell you whether it's stretched or compressed, and whether you reflect it over x, or if it's just normal, because this one doesn't have a reflection, so it's actually opened upward. If it was negative, it would be opened downward. And then we're going to identify the horizontal shift, which is in the middle, in parentheses, and we're going to do that with the opposite sign. And then we're going to identify the vertical shift, which is always at the end. Okay, next we're going to talk about the average rate of change. And when we graph these parabolas, as you can see, this one is graphed, and this is the equation that's graphed, and we can always plug that into our graphing calculators. Or you can always graph the vertex and then kind of go from there. Average rate of change, like if you can remember from the linear equations unit, average rate of change is the same thing as the slope. And the slope is the same thing as y2 minus y1 over x2 minus x1. Okay? Well, with slope is a straight line. And with your parabolas are a curved line. So there is no distinct average rate of change for a parabola. That means there's no constant rate. You have differing changes of rate throughout your whole parabola. So as you can see from and we identify these by x. So we look at the x's and say, oh, okay, between 4 and 5, so between 4 and 5, the slope is 2. But between 5 and 6, what is the slope? It's going to be 6. And then we look at between 6 and 7, so when x is between 6 and 7, so if you look at that, the slope is 10. So it changes each time. So we can't figure out like a distinct slope that's just constant. So we're only going to look at it as intervals. So we're going to look between like 2 numbers or 3 numbers each time. So like in my next example, I really don't know what the slope is, and I'm going to pick two points that it's between. So between the points 0 and 3, because those are my x's if you haven't noticed, okay, you want to identify, and you can identify this because you have a graph, right? So these are easy. So between 0 and 3, you're going to just draw a line. Okay, and then you're going to count how much do you go up and over. Okay, so I'm going over 1, 2, 3, and then over 1, 2, 3. So if my slope is 3 over 3, then it's actually 1. Okay, because you're actually going up 1 over 1. Okay, or you can always take those 2 points, and you can always plug these into the the y2 minus y1 equation. Okay, to figure out what the slope is. And that's helpful too. Okay, so for the next one, I didn't really have, an interval that I'm going to go by, but say I did want to figure out, like, what is the rate of change between where x is between -3 and -2. Okay, so between those two. So then I find, okay, well, at -3, my graph is here, and -2, my graph is here. So what is that slope? Okay, so I count from here to here. What is the slope? Well, on my -3 to 2, my slope is going to go down 2 and over 1. So the slope is going to be -2. So, I mean, those are pretty simple as long as you have a clear graph where you can just identify like the x's and then figure out what the y's are. If I wanted to do that with a table, I can always, and I wanted to use the equation y2 minus y1 over x2 minus x1, I could have always used -3 and the y value is at -1. And then I could have used -2 and the y value is at -3. And I could have plugged those points into here to figure out that my slope is 2. But it's much easier just to count on a graph. So I hope this video helped you with transformations and the rate of change of quadratics. Okay, and like or subscribe to Rollin' with Olin, and you guys have a good night.